So I just decided we'd do a whole individual section on this right here. Okay, so here's our this is Hardy-Weinberg equilibrium equation. Back to what I was doing on the previous. I showed you how this pertained to a Punnett square. Okay, in that this is equivalent of two big A's, big A, and then in the Punnett square you have a big A, little a twice, big A, little a, so there's the two, and then little a, little a. This is a Q, not an A. Okay. But what I want to do is I want to show you how that would work in a problem. How do we use this to determine in real life percentages of homozygous dominant versus homozygous recessive and the heterozygous. The homozygous recessive in a typical dominant recessive, we look at dominant recessive traits, you can tell who's recessive. Previously I'd said tasters, non-tasters, I have you taste little taste strips in class, sometimes a normal semester. And if you can taste it, you've got one dominant allele, and we call that the big T. But you don't know what that second allele is. It could be another big T, it could be a little t. It's going to be masked, so you don't know. But if you're a non-taster, you know your genotype. It is going to be little t, can't be anything else. You can't have a taster allele, so you must have two recessives. So the recessive is always visible. Okay, their genotype is known. It's the 25% big T, and 50% big T, little t you can't distinguish. Okay, but you can kind of estimate how many in the population you're going to have, okay, by using this equation. So the first problem in the homework that I would have given you to do with the lab, and I don't remember now what the trait is that it talks about, but it says you've got 360 individuals in the population that are recessive. Okay, so for whatever the trait is, and it may not even say what I can't write. Recessive. Drawing with my finger on the touchpad. It's like finger painting. Okay, so that's recessive out of a population of 1,000. Okay. So what you want to do, what you can do, is you can say, well, that means then that 640 are this, right here. Go away. But that doesn't tell us anything because we have a Q stuck in here. We can't solve for P and Q. It's difficult to solve for two unknowns. We can only solve for a single unknown. So what we're going to do is we're going to solve for Q. Because if you remember right, you spent hours in probably not biology, unless you got your homework done, you were doing it there like me. You spent hours in algebra class or at home doing homework factoring this stupid thing in all the different letter permutations they could give you. A, B, T, Z, Y, Q, S, M, N, L, J. Yeah, you got it. Okay. And you factored and you factored and you factored and you were sick of factoring. You go, why am I factoring? Why do I have to do 40 problems of this and all of that? And the reason is so that you would come to the understanding, okay, though I didn't. I'm not one of those math type people. You gotta blatantly tell me. I don't usually connect the dots on my own on some things like that, especially math. You've got to show it to me. So I didn't figure it out until biology, okay? But one of the things of factoring this that you're supposed to get out of it is that 1 minus P equals Q, and that 1 minus Q equals P, and that P plus Q equals 1. Yeah, you're kind of like, I don't know, first time somebody pointed that out to me, I was like, oh, gee, that was so obvious, but I missed it. Okay, so um, so we're going to solve for Q. And if we find Q, then if we know Q, we can know P. And if we know P, then we can find P squared. And if we know PQ, we can find 2PQ. So, all right. So just trust me here and go along with this, okay? Q squared. So if Q squared is equal to 360, okay, for this population, that's basically what it is. Well, what does that mean? Well, 360 out of 1,000. That's the percentage of the population that is. So we're going to take 360 and divide by 1,000. So Q squared is actually equal to 0.36. See that? That's the percentage of the population that is recessive. Follow me? I took 360 divided by 1,000 to get my percentage, okay, of the population that's recessive. All right, so that's my Q square. And that's your first place. That's where you always start. When I give you these questions on the test, I will always tell you, well, I might say 640 are dominant. Well, you know you've got to find the recessive. Always look for the recessive number of the population. So you take the recessive number, whatever it is, you divide it by the total population, whatever that is. It may be 1,000, it may be 500, it could be 1,748. Okay, okay. There's one of those. It's a bonus, I think, and it may not be on the final since we're not doing this on a standard lecture test. But there's one of those I give that's some actual data from an actual research data, you know, taking. And data is never nice, even numbers like this. Even if you start off with a population of 1,000 or 2,000, you're going to have individuals lost. You're going to wind up with 1,748 or something weird like that. So you just take the number of individuals that show the recessive, divide by the total population, and you get your percentage. That is Q square. Okay, that's Q square. So how do you find Q from that? Well, remember square root. Okay. And that's going to equal 0.6. Okay. So now 1 minus Q equals P. So we can find P. So this is Q. We've got Q now. Right? So Q and P. So I'm going to write those over here. Pull those over here and I'll wind up erasing the rest. But if you're following along on paper, I'll give you a little bit of time to write that down. If you didn't follow along right then and you say, oh, maybe that'd be a good idea. It might be. Because these are the steps that you'd have to use to solve a problem. And there will be, I'll guarantee, and I say that and I'll forget to put it on there, but I'm pretty sure it was on last semester's final. Tribbles. I've got a little tribble question because, I was involved in an educational fan film. We were supposed to, hopefully, going to be able to release it to teachers to use in schools to teach science through a little kind of a fan film of the original series Star Trek. I played a science officer on the ship, and it was great fun. I also helped writing one of the episodes on genetics, and I had developed problems to be used in worksheets that would be given out free to teachers who wanted to use the episodes in their classes. And it was all free, no charge, all that. But things didn't work out. In the end, we had one episode did get released. It's on YouTube if you want to go looking for it at some point. And um, Starship Grissom is I think, and there's another Grissom, but you look for the one that's the educational thing, and that's us. Anyway, the worksheets and stuff are not connected to it anymore, but the third episode, I think it was, maybe it was the fourth, was going to have the genetics, and we started filming. We did first three episodes. The second and the third were never released, and the fourth was never filmed more than like the a few scenes we got started on before things happened. So anyway, I used my Tribble question there because I think it's fun. So if you're a Star Trek fan, you will enjoy messing with Tribbles maybe on this. But yeah, there's a population of Tribbles and there's something going on. And anyway, you get to read that and work that out. But that's it. There's going to be some that have recessive trait. Okay, you find out the number of triples that are recessive and divide by your population total, and you're going to get your Q. And now I want to know, well, how many are homozygous dominant? That's PQ. My P, listen to me, P squared. Okay, so let me erase this. P squared is just going to be equal to my P squared, right? 0.4 squared. So that's equal to 0.16. And students are like, oh, that's it, I'm done. And then of course, if it's a multiple choice question on like a final, it's all multiple choice. You look, you go, that answer is not there. And you get really worried because like, what have I done wrong? You didn't finish the question. Okay. Because it's how many triples or I don't know, whatever. I've got, I think hamsters on some things, gerbils on another, got cattle. I've got all sorts of different pea plants. Okay, I can throw all sorts of different things. The population is. Uh, okay, I think I just messed up my microphone there. It doesn't really matter what. Go away, please. The organism is. It's just you're looking at your numbers. Okay, so don't let that. Don't let what trait I give you. It doesn't matter if it's fur color, eye color, anything, anything. Just don't get sidetracked with that. Focus on the number that has the recessive trait, and I'll tell you which one's recessive, or that information will have been in a previous question or something. Okay, so you should be good. Um, and you get your percentage, but we got to remember when you get this decimal, this is a percentage of the population. So in order to find out how many, and since I've been using triples, I'll stick with that. Okay, how many triples are homozygous for whatever dominant trait we're tracking here? Okay, and so you got to take your percentage times the population number. And that's going to get you 160 homozygous dominant. And that's a really long word to write out here. Finger painting. Need to get a stylus attachment if I do this a lot. Okay. All right. Then the next question, part of the question, or the next question in a sequence, if it's multiple choice, I'll probably have to put these in cascading questions. Okay, so the next one would be, what about the heterozygous? How many individuals are heterozygous? Well, that's 2PQ. Okay, so that's going to equal 2 times 0.4 times 0.6. Okay, so here we have, and yeah, if you hear the noisy birds in the background, I'm outside. So you just multiply this, and that's going to get you 0.48. Okay, and just like up here, that is a percentage of the population. So you're going to multiply by 1,000, and that's going to get you, I don't know why I started that way, 480. Wow, can't keep this the same size. Heterozygous. And remember I said before, heterozygous is heterozygous. There is no dominant or recessive on that. Heterozygous, it has one of each allele. Homozygous, you do have to state whether you've got which type of homozygosity you've got, dominant or recessive. Okay. All right. And that's it. Because if I ask you how many recessives you've got, yeah, that was given in the original problem, wasn't it? 360 right there. Now, excuse me, sorry about that. How to check yourself though. as you can come over to, scrap paper, margin your paper. If you were doing a paper and pencil test, which we won't be, we'll be doing virtual this semester, but in normal semesters, you can add all this up. 12 and 8 is 20. We hope it adds to 1,000. Okay, 3 and 4 is 7. And 2 and 1 is 3, and 7 and 3 is 10. I know that looked weird, right? Okay, how I think. All right, and so that checks you, and you know then that these numbers are realistic, okay, and that your three different groups all add to the whole, to the one, okay. So that will tell you that out of the 640 individuals, okay, that showed the dominant trait, okay, whatever that is, whatever that trait was, not a taster, non-taster, and tribbles, but whatever trait I had you follow, uh, that 160 of them were homozygous for that dominant trait, and 480 were heterozygous. Now, it doesn't tell you which individuals, okay, but it does tell you relative relationships. And why is that different? Well, because what you would expect in a population where there's not any, hasn't been any selection pressure for a long period of time, is you expect, go into this a little bit here. Well, maybe I won't erase anything. I'll probably wish I did. Okay. Does this work? Yay. Okay. Let's expected. What the Hardy-Weinberg equilibrium always predicts, and that's one of the things that the lab that I would have had you do in class drives home, and I don't think the one online really does, is that if everything is in equilibrium, if there has not been a new pressure on that population anytime recently, and the population has established equilibrium after the last selection pressure, then P will always equal Q. Okay, and we see here that P doesn't equal Q. Okay, um, that's not what's going on here. Okay, if P equaled Q, they would both equal 0.5. They have to if they're going to equal 1, and they have to. Okay, so what we can see about this population is that we are off a little bit. There's been some type of selection pressure that's upset the balance, and equilibrium is being um, uh, skewed, okay, because of this pressure that you're seeing. And actually, what you're looking at is out of a population of 1,000, you would expect, well, if this is P, if this is Q, Q squared is 0.25, right? So 0.25 times 1,000, that would be 250. We would expect 250 recessives, not 360. So we're being skewed a little toward the recessive by whatever pressure this is, okay? And also we would expect P to be 0.5. So we'd expect 250 homozygous dominants, not 160. So we've got less of the dominant trait in this population than we would expect if everything's in perfect equilibrium. Okay, so, and then of course 2PQ would be 2.5, 2 times 0.5, sorry, times 0.5. Okay, and that's going to equal, that's 0.25 times 2, so it's 0.5, right? And you take that times 1,000, and that's going to give you 500. So you expect 500 to be heterozygous. All right, so that's always the expected, and it's not what you see in any given population for any trait. Typically, it's not what you're going to see. It's what Hardy-Weinberg predicts for perfect equilibrium, but nothing's in perfect equilibrium, right? Okay, there's usually some pressure skewing things a little bit somewhere. Okay, and it depends on the trait, obviously, whether that trait is being selected somehow. one way or the other. But this is the Hardy-Weinberg equilibrium equation. This is how you work it out. The little expected, that can be a question all on its own of what does Hardy-Weinberg equilibrium predict for P, or P and Q? And you can say that P is greater than Q, Q is greater than P, P and Q are equal. That's the answer. I can throw out some other 5 options out there for you, but that's what I'm testing for, is to see if you understand that the expected is that they're equal. But then I'm going to give you situations where you have to work out populations that aren't completely in equilibrium, and we've got, yeah. I mean, this much of the equilibrium works out is that they're going to equal 1, okay, but we're not going to be equally distributed where P and Q is equal. Okay. All right. I'm going to stop this. So this is just solely a Hardy-Weinberg equilibrium practice problem or explanation problem. So I can use this possibly in the future. Students who miss that lab or miss the class where I talk about it or want to see something again, I can stick this up on D12 for that, and it'll be a standalone. So come back for more if you're in my spring 2020 class, where we need to talk some more about mechanisms of evolution.